McGill visit us this week and tell us about compute optimal neural scaling laws and how that connects to optimization. Courtney is both a professor at McGill and she has a partial appointment with Google and often collaborates with folks there. She's also a CFAR AI chair and the recipient of a Sloan Faculty Fellowship. She has done a lot of very interesting work at the intersection of optimization and machine learning, and often uses techniques from different areas, including things like probability, random matrix theory, dynamical systems, and so on. So let's please welcome Courtney. And
having me here. I'm glad I made it. The storm was a problem on the East Coast. So this is, I'm going to talk a lot today about compute optimal neural scaling laws. How many people have even heard of this? Oh, good. Okay, a couple. It's fine. Also, I know this is a very new area, so it's kind of fun and exciting to look at. And this is joint work with so one of my PhD students, Damian Fairbach, and then a group of people at Google DeepMind, and then Elliot and Gauthier, who are in Montreal. Also, please feel free to interrupt me and ask me questions. I know I use a lot of tools from very different areas, so if you're unfamiliar with that, please just ask. Okay, let me move something. So, hit OK, there you go. So what are some of the challenges we see in ML? So in ML, right, we typically are minimizing some large set of sum of functions, Fi. And the big thing here is that usually our problems are what we call high dimensional. So a lot of times we think of ML as being a lot of samples, you have a lot of data N, but actually nowadays you also have a huge number of features. So that the space for which you're actually minimizing over, the number of neurons, etc., is also as big as the number of samples. Okay, and what I mean big here, we're talking billions, hundreds of billions, probably trillions at this stage of the game. And of course, because of the fact that we're super high dimensional, we tend to use stochastic algorithms. So I'm just writing down SGD. I assume most of you have seen SGD, right? You just choose some index uniformly at random and then update your gradient by choosing the index, using that Fi, and moving in that direction. And here I'll use gamma as my learning rate. Okay. Oops. Nope, didn't like it. All right. So go back. All right. But we have to remember a few things, right? Before we actually run an algorithm on this problem, we have to choose things. So most of us are familiar with choosing the hyperparameters, like how do we choose the learning rates, etc. But actually, there's a couple of other things which are different in ML than what we typically think of in optimization, which is that you actually get to choose the space you're minimizing over. So you actually get to choose how many parameters. That's how many neurons. You get to make the architecture. You also get to choose your architecture. How many layers are you using, etc. So these are two things which we actually have to decide prior to actually running the algorithm. Okay, sorry. So how do we choose these things? So before we got really, really big models, like billions, trillion size models, we literally did this by trial and error, right? You just would run it, test the hyperparameter, see if it worked. If it didn't work, rerun it, try it again, right? But nowadays, because these things are so big, in fact, you can't do this. You just cannot, it's not computationally efficient to actually do that. You only basically get one chance at running the algorithm. Because each time you run it, it's going to take 7 months to run. It's going to cost $10 million to run. So you have to know a priori before you start running all of these things. And so in some sense, you need to know what people are now calling how algorithms scale. So how do they depend on not just, iteration counts and things, but also on the space itself, number of parameters. Okay. And so we really need a good optimization theory that sort of predicts what we see in practice, because we only get one shot. Okay, we have to choose it correctly. How do we do that? Okay, So what I've been working on over a long time is a picture I think a lot of you have seen before, or maybe you've seen before, which is basically working at how to predict the dynamics of SGD. That is to say, at any iteration of SGD, I can exactly tell you what it's going to be. Even though it's a random algorithm, I can actually tell you exactly what the loss value is. And so that's what's happening here. You see these curves, these are representing SGD. And this smooth line is actually not the mean of runs. It's literally a prediction that I can give you before you even run the algorithm. Okay? Okay. All right. So what do we mean by scaling? Okay, so when people think of scaling, what we're talking about here is we have some problem. We have a model size, or the space we're minimizing over D. And so the idea here, and you have N as samples, the idea here is you're actually wanting to think of your optimization problem as a sequence of problems that depend on D and depend on N. Okay? And scaling is about what happens as you change your model size. So as you increase D, what happens to the whole loss function? Okay? Typically in machine learning, this is done by changing both the width and the depth simultaneously. So when I say increase my number of parameters, I'm increasing both the width of my network and the depth of my network proportionally to each other. And so you get things like scaling ladders. Okay, so this is an example of a transformer scaling ladder. Okay, and if you haven't done it, it's not a big deal, but what it is here is what you see is that my attention heads, okay, this is related to my width, are going up proportionally. And as I'm increasing my width, my transformer layers are also growing. So my width and my depth is growing proportionally to each other. Okay, so you can see they're going up and they're going down. And this is the model size, 2.4 billion. That's small. The small model size. I think 1 billion, you count as large now. But that's the cutoff. Anything below 1 billion is small. Okay. But you can see that these are growing at the same rate as this. And the goal with creating these scaling ladders is that your loss function should be getting better and better as you see. Okay, so as you increase, your loss will eventually go down. And then once you fix this type of scaling ladder, right, you solve this problem with the stochastic algorithms, you still have to choose everything about it. So you need to choose batch size, learning rate, momentum, weight decay, everything as your model size is increasing. So because these things are so big and so expensive, what you have to do is you have to sort of be able to predict what the behavior is going to be at large scale. So what you would do is here you, for learning rate, say for Atom W, you run a bunch of tests on the small scales, okay? You get a good idea, you run it at the next smallest scale, etc. You go up, and then what you do is you try to fit something to it, a power law to it, so that and use that fit to predict the behavior of what happens at the very large one. Okay, so you want to be able to say, okay, if I run a head size 40, where I only get one shot at it because it's going to take, well, for us, it may take like 10 days to run. Our company is shorter, but if you wanted to run this, it takes 10 days on your compute cluster. Okay, I only have one chance at doing it. How should I choose that learning rate? Well, I'm just going to try and fit the best learning rate to it on my scale and use that to predict what I should use here. Okay. Are there any questions about this? How are you doing? Cool. Oh, all right. So that's scaling related. So how do we actually do this as a math problem? So,
question.
Yeah.
You said power law. Why is it a power law? Like, is that
it will.
this case? Or?
So with language, it will be, and I will explain why. It's actually a structure built into language itself.
Oh.
Yeah.
Cool.
So yeah. And the way physicists say is once it goes power law, it's always power law. So once you see a power law, everything becomes power law after that. So including the learning rate that you use. So I will talk about power law stuff. So let's think about this as a mathematical problem, as a framework. So what a scaling law really is, and you'll hear people talk about this, is you really want precise upper and lower bounds on your loss under a fixed architecture as a function of iterations or samples and parameters and number of neurons. So you want to know exactly how your loss changes as you change number of samples and as you change parameter size. Okay? And this really differs from previous things. You're not really in a worst case analysis. Usually worst case analysis is like, you're not gonna be allowed to do D. D is kind of fixed. You have to be able to work on all D here. Here you actually want to understand how parameters, the number of parameters affects your performance. And so again, the way you should really be thinking about this is that you have a sequence of optimization problems, each depending on n in number of samples and number of parameters. And you want to understand how those sequence of optimization problems evolves. Okay. And once you have these scaling laws, you can start to ask downstream tasks. And one of the core ideas of how ChatGPT was actually able to be like created was because they were able to answer the following question, which is that you're now currently not limited really by data. But in the language models, we have like the entire internet available to us. So data is not our limitation anymore. What is our limitation is compute. You guys all have probably encountered this. You literally don't have enough GPUs to run your program, right? We are compute constrained, okay? And that's true about these big models as well. In fact, they're limited by how much compute that there's actually available. And so what you want to be able to do with scaling laws is to take that scaling law and ask the following question. Given a compute budget, so you're only told you're allowed to use 10 GPUs, okay, for 10 days, you have a compute budget now, okay? You have infinite data, you don't have to worry about the data. Data is all available. How do you best allocate your resources? That is to say, how do you choose the best neural network, best transformer architecture, given that you only have so much compute? Okay. You're like, I've encountered this problem, right? Definitely have encountered it. All right, so how do we do this? So let's mathematically write this down as like a true optimization problem, but now in a slightly different way. So yeah.
So you have infinite data, and you're basically now assuming that all data created equal. So I don't have to worry about the fact that I'll never look at all.
Yeah.
We're not going to think about data collection, right?
We're not thinking about data selection. This is just to make the problem slightly easier. It's also probably closer to what we currently have. Compute is more constrained than data at the moment. Yeah.
The correct impression when you're modeling the loss here, is this the training law?
This will be so in this regime, because you have infinite data, the training loss and validation loss will be very close. But it's a good, and it raises it when data starts to become problems. There's a similar data like becoming constrained. Good. Any other questions? Okay, but they basically ChatGPT had to solve this problem to release ChatGPT because they had to run it for so long. They had to say, okay, if I'm allowed to run compute for 3 months, what is the best architecture I should be using? What's the biggest that I get the best loss for that if I'm only allowed to run it for 3 months? These are like big questions. We really need to know how to do this because we are really constrained in compute regard. And they were able to do that. They were able to be able to predict basically what should be the best architecture, and that enabled ChatGPT to come out. Okay? And we're still doing it. Okay? So how do we frame this as a math question? The idea is that, okay, I'm going to be minimizing an expected risk. D is my parameters because I have infinite data. I can just say as a rough estimate that compute is basically iterations, number of iterations, T times number of parameters. The cheap, okay? Let's just say up to proportion. And what you saw and what we saw is that you can then run SGD for T iterations across different Ds. You have a scaling ladder, so you have different Ds, okay? And because of this relationship between iterations and parameters, you can then plot your loss, which is normally a function of your iterations, as a function of flops, as a function of actually compute, because iterations is related to compute through this formula. And so the question that I asked mathematically written down is, given a fixed number of flops, infinite data, how do you choose D so that you get the best loss? That is, you're looking for D star as a function of flops, which is in the argmin of your loss as a function of D and flops. Okay, it's simply just a constrained optimization problem that you're trying to solve, where the constraint is that your flops is equal to iterations times parameters. Another way of asking this question is, when is it more compute efficient to continue training, or when is it better to increase the size of your problem? Okay, there's a trade-off there. So let me give you just as a picture of what's happening. So what I'm doing here is I'm running SGD for dim for D, so color the dim for D, okay? And I'm plotting based off of this thing, a flop. So this is on a log-log plot. So I'm writing my loss function as a function of flops, and flops and the loss right here. Okay, and fixing the flops means that I'm fixing some line here. Okay, and let's try to understand what's going on in this picture. Well, if D is very, very small, what happens is it's very cheap to run your algorithm. You can run it for a really, really long time. But the issue with D being very small is that you're only minimizing a very tiny space. So your model doesn't have enough expressibility to solve the problem. So eventually you just sort of level out. And of course, like if you're leveling out right here, it's just wasteful in flops to continue running this algorithm. Like it's just stopped moving the loss. So that's a bad thing. Okay, so you say, okay, well, I should increase my dimension. So let's say you do 51,000. Well, 51,000 is great, right? You have total expressibility in your model. It's got a huge number of parameters. But now every time you take an iteration step, it costs you 51,000, right? It costs you a lot to run. And because you're compute constrained, you can only run your optimization algorithm for expensive. So there's a trade-off between compute, or between number of frames and expressive. So what we see is that if you plot this thing here, the best thing is around like 12,000. E is equal to 12,000. And so you might say, what should you have done in this case? What you should have done is you should have run your algorithm, wait till it hits the stationarity point, you stop moving in your loss, and once you hit that point, you should have increased your D. It's wasteful to let it run forever in that regime. Okay. This is not the only situation. Oh, by the way, you do this for each flop and you get a curve, which is called the compute curve here. Okay, so they call this the compute optimal curve. It's like a Pareto frontier, if you like. Okay, it's not the only thing that can happen. So I just described a situation where you would run and wait till your thing reaches, your loss stops moving. Once it stops moving, you should increase. In fact, there's cases where you want to early stop. That is because your signals, the things you're trying to solve, get hit with a lot of noise, right? It's actually more costly to try and push through the noise than to stop earlier and increase the size of your problem. So you get things like this where you actually could have continued on training. Like, see, I could have gone all the way down. I could continue training, but it's actually preferential to stop way up here. This is like an early stopping, but based on compute. Okay. And so what we saw was exactly this. So basically they did an empirical version of this for LMs. And like I mentioned, this is actually what they needed to use. They needed to understand, okay, now my flop budget is like 4 months long and stuff like that. What is the D star? Like, what is D? Okay. So, yeah.
But I just want to make sure I understand.
Yeah.
Like, if they will stop and then we'll increase our model size. Like,
Yeah.
how do I make use of all the work I've done so far when I change the whole model?
So they don't, they just restart.
They just
They just totally restart. So you have, in some sense, you have to, because there's not a way to increase it.
So it's sort of, okay.
Yeah. So you really, so what you really are caring about, or you really want,
Because that's a log scale.
yeah, but also you really want this function, and you want an accurate depiction of this function, so that you know before you even run, okay, if I'm given, 10 months to run it, this is a good D to run it at. Yeah.
To clarify, so
Yeah.
the way you would run them, you would pick, 100, you would run, you restart with 200, let's say you doubled, you rerun from scratch, and so of course for the...
Yeah, but what you really do is, what you're trying to get is a picture of what this quantity is.
So you do that early D and then try to predict.
Exactly, right? If you know this curve as a function of plots, you can predict it off from the beginning. And that's what they do. And that's so, and they have to, because you only have one shot, you have 10 months, and you have to do something to get enough.
So I guess what you're gonna get is like, how do we get the
Yeah, so in some sense, yes, I'm going to talk about how do we get this. And in fact, I want to talk also about what can influence it. So like we saw model capacity is influencing it, and things like noise will influence it, but also optimization algorithm can influence it. So how do they influence it? Good questions. Anyone else? Everyone understand the question? Understand the idea? Yeah.
How are you including like width and depth with this D?
Yeah, so that's what I was saying. So you fix the architecture. So I went ahead here. So there's a way, this is not like, I'm assuming someone has already done this. So they have a scaling ladder where they say, okay, when D goes up, you typically scale width and depth simultaneously. And this is sort of like an example of how, so like 12 to 16, you see that this is proportional. I think it's three-fourths of the head size increasing to increase that. It's a good question. And how do they come up with this? That's a whole nother thing to deal with, but let's suppose they have a scaling ladder given to it. Okay. Cool, good question. Any others? Yeah.
When you draw this picture, so how do you guarantee that your model under the certain architecture that perhaps similarly under different D?
Yeah, so that's part of how they come up with the scaling ladder a little bit. They make it so that it has that, so that as you increase D, you get better performance. So how you choose how to distribute your parameters in terms of width and depth of your network, they do it in such a way that it guarantees it looks like this.
But if they look all similar, you just need to draw to choose 2Ds to draw a single line. Or you need to try different multiple.
So, yeah, this is a beautiful picture. This is a beautiful line because this is synthetic generated. In reality, this is the plots they actually do. Okay, it's a stochastic algorithm. It's bumpy. It's annoying. There's noise involved. Things like that, right? It's a little bit annoying. So you can't just really do two. That's the other thing, right? It's a little bit noisy. So what they observed in practice was something called first of all, we did not come up with this problem. This problem was a problem that was really derived from the applied side. They were really using this for LLM to be able to predict performance, okay, to try and get good Ds, okay? And we wanted to understand it from a mathematical view, okay? And so what they saw was the following. They ran a stochastic algorithm repeatedly across different parameters on a scaling ladder that they had created, okay? They plotted their loss as a function of flops. And then because you don't know, like you have to solve this problem. You actually don't know how your loss changes as iterations and parameter size changes. You only have like samples of that. So what they did is they assumed that their loss looked like a specific form, t to a power, iterations to a power, model size to a power. They empirically fit their optimization algorithm. They empirically fit the runs to this thing, found the exponents, and then re-optimized in terms of D. Okay. So that's what they did. And what they saw was that it satisfied a power law going down. That this curve and the curve for which this as a function of flops was like flops to a power. And what they really observed was in practice was what they call chinchilla scaling, which is that the way that the things were scaling by, your flops were essentially scaling by, was like number of iterations is proportional to D, or in this case, number of samples is proportional to D. Okay? So what is our goal? Our goal was to do this sort of in a more mathematical way. That was totally empirical. They just ran on LLM. That was I think Google's one. So they had a lot more compute. They could run it on bigger models, things like that. And then they tried to fit everything. We wanted to do this mathematically. So you can't solve an LLM. You can't really do too much theory with it. So what do you have to do? I'm going to take a very physicsy approach, in which is that I want to find a very simple model which gives me the same looking scaling curves and analyze that one completely. Okay, and so the simple model that we looked at is one that people use. It's a model which is you run with one pass SGD, and you have three components. You have a data component, complexity component alpha, target complexity beta, and your model parameter. And what we're going to show is that there are going to be 4 distinct phases. So there's going to be 4 different things which can influence. There's going to be 4 different distinct loss curves, compute optimal curves that you get, like the shape that you can get. And they're going to depend on how the data complexity and target complexity are related to each other. And we saw 2 of these things, and they're going to be influenced by 3 things. 2 of them we saw. Capacity as a model, that's go down, stop, you stationary, you should move. Poor feature embeddings, that's what I was describing. If you have too much noise in your data, your signals get lost in the noise, and it's too expensive to actually solve through the noise to find those signals. It's actually not as good. Okay, that's going to be poor features embedding. And then there's another area which I'll talk about, which has to do with SGD itself. SGD creates noise. That noise can obstruct your progress as well. So there's 3 things. And what we're going to show is that even for this really fake model, for a large portion of your alpha beta plane, you get a universal scaling law. That is, you recover actually exactly what was observed empirically. That is that your optimal number of parameters as a function of flops is flops to the 1. And this like sort of theoretically validates where chinchilla comes from, and possibly where we are in the language model, where things are. So what is this simple model? The simple model has to do with random features, essentially a random features model. So you have your data X, it lives in RV, you embed it via a random matrix W, and you're going to have a target B. So then I'm just going to solve the mean squared version of it, but notice that my targets don't have the randomness W. I just have the randomness W here. This W is so that I can take a data which lives in 1 dimension and map it to another dimensional space, B, okay, which is parameters. And then you run streaming SGD on it. How do you set it up? So your W is going to have entries which are normally distributed. And the key important things here is about how you generate your model and your targets to replicate this scaling. You have to generate your model and targets via power law distributions. So X, the entries of X are going to be normally distributed with J to the -2 alpha covariance. So it has a power law covariance on the data. The same thing with my targets. They're going to have a power law on my beta. Okay. And the goal in compute optimality then is just to solve this problem and to figure out what these exponents are. How does your loss as a function of flops change in terms of the exponents, and same thing D star in terms of an exponent in flops. So you're interested in the exponent on the flops. And this is exactly what produced this picture, and you can see it's really similar to the types of pictures you see in the LLMs. This is a fake model, but it's replicating the scaling. It's been used quite a bit, yeah.
Do you explain again alpha and beta, the model and complexity, and then the...
Yeah. It's because let's see, bigger alpha, it's easier to, bigger alpha, bigger beta, easier to solve. Okay, they become more spiky. Okay, and yeah, smaller alpha and beta are harder to solve.
And then how does it correspond to, say, now, not in a synthetic, but in
Real? Yeah, great question. Okay, okay. Language models have for a long time, language data itself has been for a long time known to have power law distributions all over it. Okay, so what do I mean by this? This is a synthetic version of this. So what you would do is you take the covariance of your data and you plot the eigenvalues, and you just go from largest to smallest and you plot them, and you get a curve like this when you have power law. And then the slope here depends on the exponent in your power law. Language, images all have power law distributions for their covariance. If you took two images, you took an image, formed the covariance, computed the eigenvalues for that, and plotted them, you would get things like the shapes, and it would look almost identical. Yeah.
Let me rephrase the question. Are there some natural signals that don't follow the power law? Or that would give us
so it's language in images, the strength of the power law depends on the exponent in some sense. For images, the exponent is not very strong. It's there, but it's weaker. Okay, so in that sense, it's less power law. Okay, language, on the other hand, seems to be more power law. Why? It has to do with structure of language itself. Word frequencies, this has been known in natural language for a long time. Word frequencies, you plot them, they have a power law distribution. Other things start to have power law distributions as a result of this, because syntax might start having power law distribution, all because word frequencies have power law distribution. So it's because of these properties, and it's strong. It's a very strong, like, you see the power law. And it's been proven. So this is called Zipf's law, you see. Okay. Any other? So like, in some sense, they're all, like, the power laws seem to be there. It depends on the strength of it. The language really has it. Yeah. Any questions? They appear everywhere. So if you do language things, I don't know how many people have looked at language data. Anyone? No one look at frequencies? No? If you go into it, it's just all power law. Everything you see has some sort of power law distribution. And it makes sense, right? Like, the most important words tend to show up less frequently, right? Like, if you wanted to predict what the next word is in a sentence, the Saint Bernard dog is blah. The Saint Bernard is the most important thing, and that's going to be a word which is very infrequent in there. Okay, so it appears, and so it's a natural assumption, and I hopefully have time. So how do you actually go about doing this? So I've been working in research in this area for a long time, and the idea is that you can actually predict the dynamics of the SGD algorithm under this model. So if I let K hat be the dWW transpose D, where D is a diagonal, I put J to the minus alpha, SGD actually satisfies what is called the convolution Volterra equation. Okay, and what you see is that it splits into two terms. So it's an equation. Think of it as a first order linear ODE. Okay, the loss is equal to a convolution with the loss itself again. Okay, so you see it twice, and you see two things about it. You get a term which has to do with gradient descent. That's what people call the forcing function in ODE, and then the kernel term here is actually the effect of SGD noise. So this is actually how the SGD noise hits your loss in the end. And it's in expectation, and you can write down what the forcing function is. It's just a function of the eigenvalues of this K-hat matrix. Now this K-hat matrix is random because W is still random. The random matrix with normal distributed entries. But because if you know random matrices, there's a way to replace a random matrix with its deterministic equivalent. That is, there's an equivalent equivalent deterministic matrix eigenvalues are all the same as your random, at least in distribution to your random matrix. Okay. And you can write down how those things are deterministically. And so what you can do is you can replace the random matrix with the deterministic matrix, and you get a deterministic expression for the exact behavior of SGD on this problem. Totally explicit. You can, and this is a very easy problem. Sorry, this should be T. I had K or switching between K and T in various papers. It's a deterministic expression. So you can predict a priori exactly what's going to happen. It's also basically a one-dimensional ODE.
So that is continuous time, Volterra.
This is I switched to continuous. Yeah. But it's if you want, it's just a jump. It will look continuous time. It's not actually continuous time. Sorry, this is not a continuous time.
The initial one is the discrete time,
Yeah.
stochastic. We agree.
Yeah.
The second one.
This one is also in this is also in discrete time.
Ah, okay.
It won't matter because your SGD jump, you're going to have to do so many SGD jumps, it's going to look continuous for you. But what this allows you is that you can take really large gamma. This is just full deterministic. And you don't have to send gamma to 0. This is this has to do with high dimensionality tricks here. And just to show you that you can do this, you can easily, I don't know how many people, I teach ODEs, sorry. So for me, ODEs are like, I just have to teach it. So I know way too much about it than I probably should. And my students suffer because I now know way too much about ODE solving. But you can actually solve this pretty easily. You just run a fixed point equation off of this and it solves it. Standard fixed point equation. There's other fancier methods as well. And it does a really good prediction. So in fact, you can run SGD and you can run this and you can actually, the dash lines are the prediction. Or it totally predicts well, cross dimensions, across sample sizes, everything. Okay. So now what you want to do is you actually need to start understanding this loss. You need to actually solve this Volterra equation. It's an implicit equation. And what you can show is that your loss is actually just a function up to constants, absolute constants, okay, because you want to care about how everything depends on D and N, absolute constants of the forcing plus the kernel. And then what you can write down is you're going to break down each of your forcing functions and kernels into different components, which are going to depend on the spectral property of that matrix. So this is, sorry, I'm going a little bit fast here. And each of these components is just going to be written as iterations to a power d to a power. Okay, so what are these components? So the idea is that if you look at the random matrix, I've plotted the eigenvalues of that random matrix here. And there's a deterministic formula which describes the density of those eigenvalues. And it looks like this. And you see that you have spikes. And those spikes are going to be exactly what you would get if you had just read SGD. Those components of these spikes are the SGD part. What happens is that these spikes, those are the signals that you want, but because of the random matrix, you get a little noise, and that noise causes you to put like a normal distribution around your spikes, and that normal distribution ends up getting closer and closer together, so it creates a continuum, and that's when you hit here, and that's going to become SAC component. So this is when you stop becoming sort of spiky, your signals, and your signals get really mixed up in noise. Here. And then you have a point mass of 0, which corresponds to not being able to solve the problem fully. Okay, that's the F0. And that will be their model misspecification. That's like the capacity. And then you also add on to it SGD, which adds another term here. Again, it can be just written as T to a power, D to a power, and you can solve all this. And it just has to do with spectral properties. And what you can show then is that for different alpha and beta, different parts of the forcing and kernel actually dominate. So for instance, if you're in phase 1, just FPP and F0 dominate. If you're in phase 3, KPP, FAC, F0 dominate. So what I'm saying here is that if I'm in this set of alphas and betas are your data, betas are your target complexity, you get a different shape for your loss curve. Your loss curve will first go down like other rate like FPP, then it'll switch over to a different rate and then finally level off. And then if you know this behavior, compute optimality has to occur either here or here. And this would correspond to essentially that you're running and you hit a noise regime. This has to do with the noise hitting your signals. Right here, if you stop, and here would be a capacity problem. And you can do this for each of these. And you can just solve it because you have expressions for everything. And what you recover after solving for D star, the optimal D star, is that there's a huge portion of the plane of alphas and betas, which is just universally D stars flops to the 1/2. Just totally solved. Okay. This is amazing because it doesn't depend on alpha and it doesn't depend on beta. So you don't need to know what those things are in language. You could just guess and say that I should scale like flops to the 1/2. And it's probably true for a lot. It's like a huge portion of this plane. It doesn't necessarily say that there are various things that you can do to your data so that this doesn't happen. But if you were to guess and give it to an engineer, you could just say, do this, your scaling rule. Okay? And it's beautiful. It's a whole bunch of math, and then you end up with this as your answer. Is pretty amazing. Okay? Any questions on what I did? Everyone okay? Okay. This, by the way, this flops to the 1/2 is exactly what was empirically happening in chinchilla. Okay, so it agrees with what chinchilla would have said for how you should scale your thing. Any question? Okay, I have a little bit of time. Okay, we have a little bit of time. Okay, so there's this big question now out there, which is that can you actually beat SGD? Okay, so on an LLM. Okay, so empirical evidence suggests that nothing beats SGD. Okay, nothing outscales SGD. All algorithms don't matter. The thing for why you use one algorithm for another is simply that you're optimizing for constants and not for the exponent that you get, how you should scale out. Okay, and so that makes sense. And there's been a lot of evidence. You get curves, they look almost parallel to each other. There's just shift down. So there is this question of, can you actually outscale something? Outscaling here means basically, can I get a better exponent on my D star than what I would have gotten for SGD? Okay. And the empirical says no. Okay. Anyone want to take bets? But if you solve this problem, it would be like a huge, right? Like you would not be a PhD student anymore, I'm pretty sure. So we wanted to ask this question, and we wanted to understand this on the simple model via momentum. Because in reality, people don't run SGD, they always run SGD for momentum. So I'm sure everyone here has seen momentum before. So momentum, I have my history parameter, and then I update in my parameter space with a gradient and a memory parameter. And what I was interested in is like, okay, is there actually a way to choose these hyperparameters now as functions of D, as parameter sizes, so that I can actually beat SGD? This is like, how do I actually choose hyperparameters? And why does this all come about? Obviously, we know that in convex optimization and various, strongly convex optimization, momentum is provably known to accelerate under with certain choices for your hyperparameters. We have Nesterov, we have Polyak, etc. But you have to choose your hyperparameters very specifically, and they're not dimension dependent. Okay? The problem with stochastic optimization has been for a long time is that theory says basically you have stability problems. It just doesn't work very well. And then in practice, everyone just uses Polyak with deterministic things. They literally just choose delta to be 0.1. Why? Because there was a Stanford lecture like 20 years ago that said use 0.1 for your momentum. And forever now, that is literally the default option, right, in every code base. Okay. And we use it. Why? Why do we use it? What's going on? Okay. So what I was really interested in, and I hope I have some time to talk about it because I think it's cool, is how do you choose hyperparameters for momentum, which are both time dependent, because we know that from Nesterov, but also dimension dependent. And what I'm going to talk about here is how to choose these things like dimension dependent quantities. So how do you choose these parameters in a time dependent, dimension dependent way so that you actually outscale SGD? And now, because I want to do this for language, I want to actually use the fact that language has certain structure. It has a power law structure. So I want to actually also use that I have power law distributed data going on here. So how do I choose these parameters using the fact that I have power law data to actually gain something from momentum? I'm going to run exactly the same setup, okay? The first thing you observe, which is known for a while, is that if you choose your momentum parameter constant independent of time, it's equivalent to SGD. Why is that? The reason it's true is because this, if you unravel this, is just an exponential moving in the gradients. But because SGD, the gradients don't change very much at each iteration, you forget too fast. You forget so fast that it's equivalent of basically saying it's the same gradient, the same stochastic gradient. So this is being just replaced with the exact same gradient at exactly the same point. And then you're just SGD with a different learning rate. And you actually see this. You can actually map out equivalent dynamics, plot SGD, run SGD with a different learning rate, which depends on how you chose delta, the fixed quantity, and you actually can map it, and they're exactly the same. So this is on real data, an LSTM with language data. The dotted lines are running it with momentum. SGD is the solid lines, and they're just exactly the same under this mapping between the hyperparameters. So now you say, well, I need, this already tells you one important thing. Fixed momentum does nothing. Fixed momentum in small batch settings will absolutely do nothing. Why? Because it's an exponential moving average. It kills too fast the history. And gradients don't change very much in stochastic small batch setting. They just don't move very much over time. So you know you need to have a long momentum. Long momentum here means that I need to have a time-dependent momentum, similar to, say, something like Nesterov's acceleration would have, a time-dependent momentum. Okay, but what goes wrong? What happens in Nesterov is a problem about gradient noise, okay? If you map all of these things out, and I wish maybe I had a little bit of time to do this because I think it's important, okay? If I actually look at, I can write an equivalent formulation of this where I reset gamma 1. I'm going to call, there's an equivalent gamma 1 where I can just make gamma 1 equal to 1. In order to make gamma 1 equal to 1, I have to multiply by this term here. So my gamma 3 ends up just being exactly equal to gamma tilde. So there's an asymptotic version of this. I'll put hats here. Of Nesterov, which is that this Nesterov is equivalent to doing something along this line with these hyperparameters. The problem is that you have these two, you only get to choose this gamma tilde in Nesterov acceleration, and it's the same gamma tilde. The problem is now noise. This thing is creating a bunch of noise because it has a huge history. It's building up accumulations of noise. This is not. This is exactly one single gradient. You have an accumulation of noise in one single gradient and only one hyperparameter to control it. It's not going to work. You can't do it. And in fact, it's exactly what you see. You see on problems with language, with power law distributions of Nesterov, it just diverges. there's no choice of hyperparameters with which work, and it's simply because you only have one, you end up killing one of these two terms, and you need both of them for it to work. Okay. Is that okay? Oh, now I have things on my board. Okay. So how do you start doing this? I hope I have a little bit of time. By the way, please ask me, because I think this is really important, and people don't know this about momentum. I think it's very, very intuitive what's going on with momentum in the stochastic setting. So what you can do and what we were interested in is, okay, you need to have two hyperparameters. No matter what, you need a hyperparameter to control your one stochastic gradient. You need an extra hyperparameter to control your momentum, and you need long momentum, right? We need all of them, okay? So now it becomes the question, how do you choose these guys? So you can first start off by saying, I'm going to choose this gamma 3, the thing that controls my momentum, to be constant. That is to say, it doesn't depend on t here. It can depend on d, but it can't depend on t. And if it depends on d, you can show that what you need is 1 over d. That's what you need in order to go into control. Problem with that, that's for stability. You just need 1 over d so the algorithm is stable. The problem with that is that it's 1 over d, if you use 1 over d, you've made this very, very small at initialization in early time. So this is not contributing in early time. In fact, you need at least d iterations in order for momentum to kick in. Just because you killed this so small, you made this tiny, okay? And you can see this. So here's the Dana constant. What you can see here is actually that it goes, so SGD is the blue, green is Dana constant. It goes here, you can hit t is equal to d, and then it diverges off the moon. Up until t is equal to d, they're identical. So now you might say, well, can you do better? And it turns out you can do better. You can choose your learning rate to just be time dependent, but use the power law exponent of your data. And you can choose it to be exactly 1 plus t to the minus 1 over 2 alpha, and you get an edge of stability type effect. So what you can do is you can look at learning rates, which are 1 plus t to a power, vary this power. And what you see is that for powers which are too small, you diverge. And for powers which are too big, you converge, but you get worse rate of convergence, and it's continuous all the way down to SGD, which is the purple line. What this 1 over 2 alpha is exactly the edge here. It's exactly the edge. The same thing can happen in D. If you look at gamma 3 with D to a power and you vary this power, for two small kappas, you diverge. For two large, you converge, but it's slower. And then this is actually just hugging that line. But I'm really, really using the fact that I'm power law distributed data. Okay. This okay? And so you get this. So what this is sort of kind of saying, and you see acceleration. So data decaying sort of fixes this problem of like, okay, like you have to wait D steps for anything to happen. Now this thing is actually just straight up hugging and actually accelerates. So you can see it goes down much, much faster, provably faster. Okay. When this kappa 3, so when this quantity becomes 1, you just become SGD. So in some senses, kappa 3, 0 would be like Nesterov, and full batch Nesterov. 1 is like SGD. You want something in between. Okay. And the optimal one will be dependent on the power law. Okay. I'm gonna skip all this. You can do the full analysis of all of this. You see acceleration, which is you actually see outscaling, so you can actually get better exponents on your compute optimal curve by doing this, by exploiting power law. Yeah, I'm really exploiting power law distributions here. Okay, but it's pretty cool that you can do this. You can explicitly write down how much acceleration you get. So if you were to just do SGD, you would get this rate. If you do Dana decaying, you get an extra factor here, which is dependent on your choice on the exponent for the time. So you gain a little bit and exactly interpolates between full batch Nesterov and SGD. So just a total interpolation between the two. I won't say anything, but basically I'm running out of time here. This is an example where you can choose any power of D, any power of T. All of these on this line get convergent algorithms. The optimal one is chosen here. If you know schedule 3 SGD, that's actually exactly equivalent to kappa, my kappa 3 equal to 1. It will actually always produce SGD behavior. Data decadence is up here. And basically what we believe is that as you increase batch, this red line, which is the line for stability, decreases down until you get to Nesterov. It's just like a parallel line going down. It's literally extrapolating it. But this is the best you can do in a very small batch behavior. Okay. I just wanted to say that this thing worked on language data sets on LSTMs, which is absolutely amazing. One of the things I'll say in a second, you don't know, like for kappa 3, if you want to use this, you have to know the power law exponent. You don't know it in practice. You don't know the data exponent. But because you can sweep for different kappas, and you can see like it blows up, it actually, and you can track when it starts to blow up, that can tell you your kappa 3. So on the PLRF one that told you how to do it, you actually see a similar behavior on language models that if you vary the kappa 3, at some point it blows up, and you just want to find where it stops blowing up. Okay, that's how you would sweep it in language. This thing transfers. So once you figure out this kappa 3 on a small model, it turns out it just works for larger models. It's dimension independent. So you can just sweep it, find out the small one, use it on the large one, and it works. It was pretty amazing, this. And yeah, it's just working. I want to say something if I have a tiny bit less time in here. Sorry, this result will come out in exactly 24 hours. ICML will finally be over. Okay, so one of the things people always ask about is this is really SGD and momentum, right? This is really the comparison. Obviously, we use a lot with Atom on these things. So how do you can incorporate this into Atom? So you can do, we've been working on this with Atom. So what you want to do is you want to choose your beta 1, so it's going to be log momentum time, if that makes sense. Then you want to choose your damping sort of coefficient to be 1 plus t to the 1 minus kappa. You might say, why is there a 1? It's because I use an EMA here. In typical momentum settings, you don't have this EMA thing. So you gain an extra power here. And it worked. We are really excited. So we did this on a transformer scaling model. And what we showed is that there is a kappa. It's roughly 0.85. Why 0.85? Don't know. Maybe it has something to do with some structure and language itself. This is on fine web data. We did it from 45 million to 2.6 billion parameters. We scaled it, and what we saw is that it gained a compute efficiency of 40% over Atom W baseline. So you got 40% savings just by literally choosing this property much better. It has the same hyperparameters as Atom, number of hyperparameters, by the way. You don't even have to change the architecture. It's just a matter of like choosing the schedules properly. So yeah, it was really cool. I mean, I would love to do bigger, but I don't have compute for 0.6 billion. That's max for me. Anyway, I want to thank you, and this is work of 2 papers. So if you have questions, I'm happy to answer them. So thank you. Sorry, yes, sorry.
Very cool. I had a question about the scaling laws in the beginning.
Yeah.
So in that setup, the data point like kind of match the target. Like the first entries are big and the last entries are small.
Yeah.
It's like a key feature or
Yeah, it's to create the scaling law. It's not quite matching. You'll not be able to solve it because there's no W here. So there is a mismatch in the thing because your targets are X transpose V. There's no W matrix here.
I guess I mean that the order of the indices. So the first entry in D is the biggest, right? And the first entry in X tends to be the biggest.
Yeah, except that then it gets hit with a random matrix, so that screws up the ordering.
So could I reorder all that XJs and it would?
So you can do that, but it's essentially like killing off this random matrix here. And you want this random matrix because you want to have two parameters. You want to decouple the space for which your data lives in, which is something you can't control, from the space where you can control, which is your number parameter. So the W is a little bit funny. So a great question is like, we just use normal distribution, but if you did like feature learning where you might change this, it might look more like what you're saying. Like it might evolve over time to have like a shape to the W movement. And that hasn't really been explored. Does that sort of make sense? Yeah. Okay. We can talk to. Yeah.
In the random features model setting, there
Yeah.
were some regions in the alpha beta plane where optimal